Open up your kitchen cabinet, pick up a simple shaker of table salt, and you are holding the future of global energy. For the past 2 decades, the entire modern world has been completely dependent on a single, silvery-white metal, lithium. From the smartphone inside your pocket to the electric vehicle parked in your driveway, lithium-ion chemistry has monopolized our lives. But as the global demand for clean energy reaches unprecedented heights, our absolute reliance on lithium is pushing us toward a breaking point. The supply chains powering our green transition are deeply fragile, environmentally destructive, and tangled in intense, volatile geopolitical resource wars. But right now, a quiet revolution is taking place inside the world's most advanced battery manufacturing facilities and scientific laboratories. Engineers are successfully breaking the lithium monopoly by turning to one of the most abundant, inexpensive elements on Earth, sodium. The exact same chemical foundation found in common sea salt is about to completely rewrite the rules of energy storage forever. We are entering the era of the sodium-ion battery, a breakthrough technology that will radically democratize power for the entire planet. Like and subscribe to the channel visual link if you want to master the cutting-edge science and technology trends reshaping tomorrow. To understand why this shift is so profoundly urgent, we have to look at the severe limitations of our current lithium infrastructure. Lithium is highly effective at storing energy, but extracting it from the earth requires an absolutely staggering environmental sacrifice. To mine just 1 single ton of lithium, mining operations must evaporate roughly 500,000 gallons of precious local water. In arid regions like the South American Lithium Triangle, this massive water consumption severely drains the water tables of local communities. Furthermore, the processing supply chain is heavily monopolized, with a single country controlling the vast majority of global refining capacity. This extreme geographic concentration leaves car manufacturers and national power grids dangerously vulnerable to sudden trade embargoes and price spikes. Sodium, on the other hand, is completely ubiquitous, making up nearly 2.6% of the entire crust of our planet. It can be extracted easily from seawater or vast underground rock salt deposits found abundantly across every single continent on Earth. This means any nation with a coastline or a salt mine can easily secure its own sovereign supply of raw battery materials. By switching from lithium to sodium, we completely eliminate the toxic mining practices and volatile geopolitical choke points of the past. If you are fascinated by the hidden material science and supply chain shifts driving the electric vehicle revolution, hit that like button. But the benefits of sodium-ion technology extend far beyond simple geography. The underlying physics reveals massive structural engineering advantages. Inside a traditional lithium battery, liquid electrolytes are highly flammable, creating a persistent risk of dangerous thermal runaway catching fire. If a lithium cell is punctured, crushed, or overcharged, it can trigger a violent, self-sustaining chemical blaze that is nearly impossible to extinguish. Sodium-ion batteries utilize a significantly more stable chemical architecture that is inherently resistant to catching fire or exploding under stress. They can be safely punctured with steel nails, completely crushed, or heated to extreme temperatures without ever triggering a dangerous thermal event. This absolute safety profile makes them an incredible choice for powering passenger electric vehicles and massive residential energy storage systems. Furthermore, sodium batteries possess a stunning physical superpower that completely solves the biggest complaint of current electric vehicle owners: winter. When temperatures drop below freezing, traditional lithium-ion batteries lose up to 40% of their driving range and charge painfully slowly. This happens because the liquid lithium ions become incredibly sluggish, struggling to move through the internal structure of the battery cell. Sodium ions maintain excellent mobility even in sub-zero environments, allowing the battery to retain over 90% of its energy capacity at -20 degrees. Don't forget to subscribe to Visual Link and turn on notifications so you never miss our weekly breakdowns of critical deep tech breakthroughs. This incredible cold weather performance means electric cars powered by salt will remain fully reliable during the harshest northern winter blizzards. Additionally, sodium batteries can be completely discharged down to 0 volts for shipping and storage without damaging the internal cell components. Lithium batteries must always maintain a partial charge during transport, creating a continuous hazard of fire during overseas cargo shipping. The manufacturing transition is also incredibly seamless because sodium-ion batteries can be built using the exact same factory assembly lines as lithium. Battery giants don't need to spend trillions building brand new infrastructure. They simply adjust the chemical inputs on their existing machinery. Even better, sodium cells utilize abundant aluminum for their internal current collectors, completely eliminating the need for expensive, heavy copper. This material substitution slashes the baseline manufacturing cost of a sodium-ion cell by nearly 30% compared to lithium equivalents. Yet, despite these massive advantages, early critics pointed out one specific weakness that kept sodium inside the laboratory for years: energy density. Because a sodium atom is physically larger and heavier than a lithium atom, it takes up more space to store the exact same electrical charge. This lower energy density means a sodium battery pack is naturally heavier, making it challenging for ultra-long-range luxury electric vehicles. But modern engineers have developed advanced molecular configurations, like Prussian blue analogs, to pack sodium ions closer together than ever before. These structural breakthroughs have boosted sodium energy density to the point where it perfectly matches the requirements for standard city commuting cars. Major automotive manufacturers are already launching affordable, mass-market electric hatchbacks powered entirely by these low-cost sodium-ion battery packs. These affordable salt-powered vehicles will finally bring clean transportation to millions of everyday consumers who cannot afford expensive luxury EVs. But the absolute biggest impact of the sodium revolution will not be seen on our roads. It will be seen directly on our urban electrical grids. As the world transitions to intermittent renewable energy sources like wind and solar, we face a massive, critical storage problem. The sun doesn't always shine and the wind doesn't always blow, requiring massive stationary batteries to store power for entire cities. Using expensive lithium for city-scale grid storage is economically unviable and wastes precious material needed for long-range transport. Sodium-ion technology provides the ultimate, cost-effective solution for storing terawatt-hours of clean energy safely right next to major population centers. Vast warehouses packed with thousands of stable, inexpensive sodium battery cells are currently scaling up to back up regional power grids globally. They capture excess solar energy during the middle of the day and smoothly release it back into the city during peak evening hours. This massive deployment of grid-scale salt batteries will finally allow humanity to completely shut down dirty, coal-fired power plants for good. We are moving toward a highly optimized, bifurcated energy landscape where different chemical elements serve their absolute best structural purposes. Lithium will remain highly valued for high-performance applications like aerospace engineering, heavy long-haul trucking, and premium long-range vehicles. Meanwhile, abundant, safe, and inexpensive sodium will become the tireless workhorse powering our daily city commutes and localized utility grids. The future of energy is being democratized, shifting away from scarce, concentrated minerals toward common elements found everywhere across our world. True technological progress occurs when we learn to work in complete harmony with the natural abundance of our planet's chemistry. As you look out across the rapidly evolving landscape of clean technology, remember that true innovation is often hidden in plain sight. We spent decades searching for exotic, rare materials to solve our energy crisis, only to find the ultimate answer right on our dinner tables. Claim your understanding of these hidden elemental shifts, look past the loud headlines, and respect the raw material reality of our progress. The transition to a sustainable world is fundamentally anchored to scalability, and nothing scales better than the simple chemistry of salt. We must remain analytical and supportive of these deep laboratory transitions as they scale up to reshape the global industrial complex. The companies and nations that master the production of sodium-ion infrastructure will dominate the next century of clean technology manufacturing. By embracing the abundance of sodium, we can build a resilient, safe, and truly global clean energy web that leaves no community behind. Keep your eyes on the factories, monitor the rapid shifts in battery chemistry, and stay completely grounded in the physics of reality. The road ahead is paved with abundant materials, anchoring our sustainable dreams to the everyday resources readily provided by the Earth. Stay curious, stay energized, and keep uncovering the massive physical forces driving our digital future. So hit that like and subscribe button for visual link.